Okay, so let's get ready for a pretty long video. Organic compound naming. So there's like several major classes of compounds that we're going to be discussing, and the first class of those is the alkanes. And your normal standard straight chain alkanes are going to be made of only carbon and hydrogen in the ratios of the following: CnH2n plus 2, where n is any whole number. So I created a table here of n from 1 to 4. These are the names and the formulas of a couple of alkanes. So you can see they all follow CnH2n plus 2. So for example, for methane, that has n equal to 1, so C1, and H 2 times 1 is 2 plus 2 is 4. And you see they all follow that formula. And if you want to make bigger alkanes, which have more carbons in them, you're just going to use your standard Greek naming prefixes for those. So you might notice that meth, eth, prop, and bute are different from the normal Greek naming prefixes from 1 to 4, but from 5 onwards, they're going to be the same. So 5 carbon alkane is going to be pentane, 6 carbon is going to be hexane, and so on. But what do these alkanes actually look like? So we can actually draw them based on their name. So if I was given, for example, propane, as soon as I see prop as the prefix, I know that that means we have 3 carbons. So we're going to draw 3 carbons. And so a carbon wants to have 4 bonds coming off of it, 4 single bonds. Or it can be a double bond and 2 single bonds, or a triple bond and 1 single bond, just any combination that lets it have a total of 4 bonds. So these carbons, you have to bond them to each other. So they're bonded to each other. And we know that alkanes contain only single bonds, so we don't have to worry about a double or a triple bond. So now we have our 3 carbons in propane, and now we have to have 8 hydrogens. And hydrogens can never be the central atom in an organic compound, because a hydrogen can only form 1 bond, because it only has one more bond that it can form. So in order to place our hydrogens, we're going to have to bond them to carbons. Because if you bind a hydrogen to a hydrogen, then you're creating a dead end, basically, and you can't extend the molecule out further. So let's draw our 8 hydrogens. We have 1, 2, 3, 4, 5, 6, 7, and 8. Oh, we connect all of these with a single bond, and that right there is propane. And we can look at our structure to look for some obvious flaws, such as, do all the hydrogens only have 1 bond? Oops. Yeah, now that's propane. And do all of the carbons have 4 bonds coming off of them? And we see that they do, so this structure is possible. So one important thing to note about alkanes is that they're going to combust and form carbon dioxide and water when you react them with an excess of oxygen. But the alkanes are not always just simple straight chain alkanes. We can add what's called functional groups to them to replace the hydrogens on them and give them a little bit more variety. So we can add actual hydrocarbon chains to the hydrocarbon chains. So we would just change the ane suffix that they have. Like, remember, we have methane, ethane, pentane. We would just change that to -il and take 1 hydrogen off of it. So an example to that would be the methyl group. So we know that regular methane is CH4. So if we take off 1 hydrogen, it becomes CH3, and that is the methyl group. Same thing with the ethyl group, and you could really add any number of carbons to that. So an example of that would be if you had just a normal methane or an ethane, for example, and you just drew it like that, and with all your hydrogens, but you took away one of the hydrogens and you changed this to a CH3 group. Now this would no longer be just ethane. We've modified it. This would be methyl ethane. So that's how we add functional groups. And there's also other functional groups we could add, which are the halogens. When you add a halogen, so that would just be taking one of these and replacing it with, instead of a CH3 group, with a halogen. So for example, a bromine. And that would be bromoethane, because we have a bromine. You just add O to the stem of the halogen name, so fluoro, iodo, bromo, etc. And that's how you add that to the beginning of your alkane base word, and that's how you determine what to call it. And this type of compound is actually called an alkyl halide. It's going to be all of your alkanes that have halogens attached to them. Class of compounds that we're going to be discussing is the alkenes, and these have a generic formula of CnH2n. So you're going to have twice the number of hydrogens as carbons. And these, unfortunately, CH2 does not exist. And just think about a second about why that might be. And the reason is because, remember how I said that carbon needs to bond with 4 other atoms in order to be complete? Well, CH2 would have carbon bonding only to 2 other atoms, 2 hydrogens, and that carbon's valence shell would not be full, so that's why this compound does not exist. So from N equals 2 onward, we have our alkenes. And the reason they're called alkenes is because we named them just like the alkanes, except we replace ane with ene. So we have ethene, pentene, butene, and so on and so forth. And these are what we call unsaturated hydrocarbons. And you may have heard of saturated and unsaturated fats, and this is really the same concept. So these are unsaturated because they have double bonds in them. Versus, remember, the alkanes only had single bonds. These are going to contain double bonds. And that means they don't have the maximum possible number of hydrogens. You'll see these have less hydrogens than the alkanes. So that's what makes them unsaturated with hydrogen. And there are isomers possible with the alkenes. So what an isomer is a molecule that has the same formula as the other molecule, but its structure is different if you draw it out. So there is a specific system for naming these isomers. So I'm going to show you how to name a butene with 1 double bond. So suppose we have butene. Let's draw this compound. Okay, so we see the prefix but, and that is going to mean we have 4 carbons. So let's draw out our 4 carbons. Let's draw it over here. 2, 3, 4. And we see ene. That means we're going to have a double bond. But first, let's go ahead and fill in all of our hydrogens. So this would be a butane. It has the maximum possible number of hydrogens. It is saturated. But a butene is going to have a double bond. So there's 2 possible options now to draw the butene. We could put the double bond here and get rid of this hydrogen. That's a butene that has 1 double bond and it has 4 carbons, right? Or we could put that back and we could draw the double bond here and get rid of this hydrogen, right? And that right there, yeah, that's still a butene, isn't it? That's weird. So how do we know which butene we're going to be drawing? Well, the way that we do that is we number our carbon-carbon bonds that we have in this molecule. So you see here that this is a carbon-carbon bond. That's number 1, this is number 2, and this is number 3. Remember, we do not number the carbon-hydrogen bonds, only the carbon-carbon bonds. And then we figure out where the double bond is. The double bond is on carbon-carbon bond number 2. So that means we're going to call this particular isomer 2-butene. That is just telling ourselves where that double bond is. And if it were on this carbon bond right here, if this was a double bond, that would be 1-butene. But what if it was on this one? Would that be 3-butene? And the answer is no. because if you think about it, one butene, if you just flipped it over like that, it would be here. So that's not a unique, different isomer. That's just you flipped the molecule around. So this would still be one butene. So that brings us to the rule that when you're numbering, you might wonder whether we're numbering from left or to right or from right to left. Well, it depends. You want to number so that you give your double bond the least possible number. So if I have the options of calling it 1-butene or 3-butene, I'm going to call it 1-butene. And that's going to apply to any functional group whose location you're indicating, any double bond, triple bond, anything. You're always going to want it to give it the lowest possible number. So this final class of hydrocarbons that we're going to be talking about is the alkynes. And their formula is going to be CnH2n-2. And they actually have a triple bond, so that's why we're reducing the number of hydrogens further by 2. And they are also unsaturated. And you're going to name them just like we've named the alkanes and the alkenes. We're going to have ethyne, pentyne, butyne, and going on. So, how do we draw an alkyne? So I'll give you guys an example of 1,3-butadiene. So this looks a little bit complicated, but let's just do it step by step. So the first thing we see here is but, and that means we have 4 carbons. So let's draw our 4 carbons. And we see diene. So up until now, we've only worked with there being 1 double bond or 1 triple bond, but the diene indicates that we have 2 triple bonds. Just like if we just had an ine, that would be 1. If we had triene, that would mean 3 triple bonds, and so on and so forth. So we have 2 triple bonds. Where are the 2 triple bonds? Well, that's what the 1,3 is telling us. So we just put 1,3 to indicate there's 2 separate locations for them. So let's go ahead and number our bonds. We have 1, 2, and 3. And it's telling us that 1 and 3 are the bonds that have our 2 triple bonds. So let's put a triple bond here and a triple bond here. And then we can fill everything else up just as if it were an alkane. So this is a single bond since it was not indicated otherwise. And we need to look at the number of hydrogens that each carbon needs. So this guy already has 3 bonds. He needs 4, so we're going to give him a hydrogen. This carbon already has 4, so that's good. And this carbon also already has 4. This carbon has 3, so we're going to give him another hydrogen. And so that right there is going to be 1,3-butadiene. So there is one thing that we can do for our larger compounds to make them a little bit less cumbersome to write, is just to take off the hydrogens right here and just leave empty bonds. And this is what's called the hydrogen suppressed molecular structure. That's just the molecule with everything in it except for the hydrogens. So this compound right here is still 1,3-butadiene. We just assume when we see a bond that has nothing connected to it that this is going to be a hydrogen. Because with some of our larger organic compounds, we have so many hydrogens that we really just don't want to draw them all. This is mostly just for convenience. So one thing about the alkanes is that it's possible to have cyclic alkanes. So instead of them being just a straight chain of carbons, they curl around and the end carbon attaches to the first carbon and you have a circle. And this ends up removing 2 hydrogens. So these just are going to be your normal alkane names with the prefix cyclo. So for example, cyclopropane. And you can only obviously make a circle with 3 or more points, so it's going to start at propane and onwards. So the way we would draw cyclopropane is that we would just make a ring of 3 carbons instead of it being a straight chain. We connect these to each other and then give them all the hydrogens they need, or let's just do, in order to make their valence shells full. So this right here is going to be cyclopropane. And we can also add functional groups to these if we want to. So if, for example, I wanted to take this hydrogen off and I wanted to add a bromine, for example. So here, how do we know which carbon that this is going to be on? Well, there's like different isomers once again, and when you're naming them, you always want to start with the lowest possible number. So you're going to number your carbon-carbon bonds, and the carbon that's going to be number 1 is always going to be the one with the functional group. Like, you want it to be 1 bromocyclopropane. You do not want to number it as any larger number because it's a circle, right? You can start from any point you want on that circle. You want to start from the point that will let you give it the lowest possible number. So this would be 1 bromocyclopropane. And I arbitrarily chose this to be 1 just simply because that's where my bromine is. So there are some more complex ring structures we can look at, and those are going to be called the aromatics. And they're called that because they do have aromas. And their generic formula is going to be CnH2n-6. And the simplest form of an aromatic is benzene. And when you have 2 benzene rings attached together, that's going to call it a naphthalene. And when you have 3 of them attached together, that is an anthracene. So the way that a benzene looks is it starts with a base of 6 carbons in a ring. So we're going to draw 6 carbons. And it's going to have both single and double bonds. So we first draw all our bonds, and they're alternating single and double. So here's double, here's a double, and here's a double. And there are possible isomers for aromatic compounds. So for example, if I wanted to add a methyl group, a dimethylbenzene is called xylene, that's its more common name. And they can be an ortho, meta, or a para isomer. So first I'll put 1 methyl group on. And suppose we arbitrarily call this carbon number 1. And then we add our second methyl group here. This would be an ortho isomer, and we would call this O-xylene. But if we took this methyl group and moved it from here to here, and it was now 2 carbons away, here's our methyl group, this would be a meta isomer, and that's going to be M-xylene. And if we take this, there's one more possible location for it. It's all the way the opposite side from the other one. Here we put that, and this is going to be P-xylene, or para isomer. And benzene actually, quite interestingly, has a resonance structure. So these, you can see there's 3 single bonds and 3 double bonds, but it's actually not a solid single or double bond. Each bond is constantly switching places. So this is switching from being a single bond to a double bond, and this is switching from being a double bond to a single bond. So this is what we call a resonance structure, and the way we would indicate that is by putting an arrow and saying this goes back and forth between this, where this is a double bond, this is single, double, single, double, and single. So you see that this bond goes rapidly back and forth from the 2 stages, so it has a resonance structure. It's actually a hybrid bond in between the length of a double and a single bond, so it's never going to be either one or the other. So now let's talk about the carboxylic acid. So these are going to be organic acids that have a COOH group, where you have a carbon that's double bonded to an oxygen that is single bonded also to an OH group. And they're going to end in oic acid. So if you had one with 1 carbon, that would be methanoic acid, 2 carbons would be ethanoic acid, and so on. Or you could alternatively begin the compound name with carboxy. So carboxymethane, carboxyethane. So how would we actually draw a carboxylic acid? For example, a really common one is ethanoic acid or acetic acid. And so how we would draw this is we see ethane, so we automatically draw our 2 carbons. And we see oic acid, so that means we know that there's going to be a carbon double bonded to an oxygen, single bonded to a hydrogen. This is our COOH group that we have, a alcohol group, I mean, not a hydrogen. Yes, and that is going to be bonded, and we fill in the rest of our blanks with hydrogens. So that right there is going to be ethanoic acid. And you can extend the chain of carbons as long as you wish and make propanoic acid, butanoic acid, and so on. So now let's talk about another class of compounds, the amines. So the amines are going to be bases because they're nitrogenous compounds. So they have an NH2 group. So remember how I said hydrogen can only form one bond and carbon can form 4 bonds? Well, similarly, nitrogen can form 3 bonds. So it can be found, this amine is going to be found at the end or attached to any point really in a hydrocarbon chain. So you would just call the compound an amine. So you could have a methylamine or ethylamine or any really number of carbons with an amine. So another class of compounds we have is the amides. So this is going to be a carboxylic acid group with an hydrogen replaced with NH2. So the way that it would look is like this. So this looks like a normal carboxylic acid, except down here, instead of the usual hydrogen, we have an NH2. So this is an amide. So we just, in order to name these, we replace the name of the parent acid, the oic acid part, with amide. So for example, if we had ethanoic acid, but we replaced the hydrogen at the end of the carboxylic acid with an NH2, we would change that to ethanamide. So now let's look at the alcohols. So alcohols are going to be any compound that ends in the suffix -ol. So we can have methanol, ethanol, propanol, butanol, and going on from there. And they're going to have an OH group attached to the end of them. So for example, methanol would be a 1 carbon with an OH group and its hydrogens. And that's simple enough, right? We can add any number of OH groups, so that would be a diol, a triol, and so on as well. So with the C double bond to O group, the carbonyl group, there's 2 possible types of compounds that we could have. We could have a ketone, which is when the C double bond O is in the middle of the hydrocarbon chain, or we could have an aldehyde where the C double O is on the end of the chain. So the way we named aldehydes is the ol at the end of the alcohol is changed to an al. So we have methanal, ethanal. And with ketones, we just simply add -one to the end of the stem. So butanone or propanone. So how would we draw butane 2-one? So the 2 in front of the -one tells us that there are 2 carbonyl groups. And the fact that it's a ketone tells us that these are going to be, or the carbonyl group is on the second carbon. Yeah, that's what I mean. I'm sorry. And the carbonyl group is going to be in the middle of the chain since it is a ketone. So let's draw this. So we see butane, so that automatically tells us we have 4 carbons. And let's number our carbon-carbon bonds. So we have bond 1, 2, and 3. And it tells us that bond 2 is the one that has the carbonyl group. So this bond right here is going to have the C double bond O group. And of course, a hydrogen also comes with that. And we're going to finish this butane molecule, adding our hydrogens to it. And that right there is butane 2-one. So now let's talk about ethers. So an ether is basically an oxygen that's in the middle of 2 hydrocarbon groups. So this right here is going to be dimethyl ether because here's a methyl group, here's a methyl group, and they're separated by an oxygen. So well, you can also have 2 different types of hydrocarbons on both sides of the oxygen. You could have a methyl group here and an ethyl group here, and then that would be methyl ethyl ether. So you always name the ether with the shortest hydrocarbon chains named coming first, then the longer one, and then ether. So this one, if you have 2 of the same, of course, it would be dimethyl ether or diethyl ether or so on. So the final type of compound that we're just going to touch on a little bit is the ester. So an ester is formed by reacting an organic acid plus an alcohol, and it is a compound with a COO group somewhere in the middle of the molecule. So that's all for today. I hope you guys enjoyed the organic compound nomenclature video, and please come back next time for radioactive decay.